I'm Zhufan Wang from Tsinghua University, and I'm happy to introduce you Dayu, a recovery protocol achieving fast and low interference data recovery in very large storage systems. And this is a collaboration work from Tsinghua University, the Ohio State University, and the Alibaba. When node fails, replica-based storage system will replicate lost chunks from other replicas. To achieve this, a data recovery protocol should determine a transmission source, a destination, a bandwidth for each lost chunk. We call that recovery task scheduling. An ideal scheduling algorithm should achieve at least two goals. First, it should be able to generate high-quality recovery plan which allows the system to recover fast with small impact on the foreground traffic. And then second, the scheduling algorithm itself should be fast enough so that it does not become the bottleneck of the recovery. To understand how well existing protocols can achieve these two goals in a large system, we analyze the trace collected from AliCloud's online underlying storage system Pangu. Pangu has a similar design as GFS and HDFS and so on, and our observed system is deployed on a cluster about 3,500 nodes. We summarize our observations. The first observation is a huge scale. The cluster has about 3,500 nodes, and each node stores an average about 250,000 chunks. This means scheduling is heavy in terms of computation. When node fails, there are 250,000 chunks of data need to be scheduled, and each chunk has about 3,000 nodes as candidate destinations. The second observation is that the resources available for recovery are rich, as the foreground only uses about half of the bandwidth. If the recovery can use all idle bandwidth, the ideal recovery time of a single node failure is short, averagely only 51 seconds. And this suggests that a scheduler should complete quickly so that it does not become a bottleneck. The third observation is the imbalance in the system. On the one hand, in the short term, the foreground bandwidth utilization is distributed unevenly across nodes. Okay, there are more than 90 cases where the COV of the foreground utilization is greater than 40%, indicating that significant imbalance. On the other hand, replicas of chunks on a given node are distributed unevenly across nodes. Some nodes have a larger number of recovered available data chunks. These two imbalanced distribution pose a challenge to scheduling quality. Fourth, the foreground traffic changes dramatically in some cases, as the cases outside two red lines in the below figure. Okay, this requires a scheduler to adjust the scheduling plan quickly when it observes significant change in the foreground traffic. The above observations show that scheduling algorithms need to compute large and complex problems within seconds, but none of existing approaches meet these goals. Simple algorithms like randomized solutions finish scheduling quickly but generate low-quality results. And conversely, complicated algorithms take a long time to produce a high-quality solution. And we like to find an approach here. To this end, we designed a fast and low interference data recovery called Dayu. It's a name from a famous flood control expert in Chinese legend, and we wish this protocol could also control the flood of recovery well. Dayu solves this problem by designing completed algorithms with good scalability. Dayu uses a centralized scheduler which schedules a task using a Timeslot-based protocol, and we further proposed 4 key techniques to achieve high speed and high quality in one time slot. As mentioned before, Dayu is a Timeslot-based protocol. It divides the entire recovery times into slices. A centralized scheduler collects the latest state of the cluster at the beginning of one time slot, then schedules the tasks which are expected to complete in one time slot. To fully utilize the bandwidth, Dayu overlaps multiple time slots. Okay, time slot-based scheduling provides two benefits. First, Dayu only need to schedule a subset of tasks in one time slot, which reduces the computation overhead. And then second, when foreground load changes dramatically, Dayu can adjust its plan in next time slot. Next, we present the scheduling algorithms in one time slot. Recall that the scheduling algorithms should determine a transmission source, a destination, and the bandwidth for each task. To make these decisions and achieve high-speed and high-quality scheduling, Dayu propose 4 key techniques. And let's look at them one by one. Dayu uses these first key techniques to selecting working nodes for each recovery task. After simulation experiment, we decide to use a greedy-like algorithm to choose working nodes. That is, for each task, the scheduler chooses a pair of source and destination node with minimum expected completion time. That is, find nodes with smallest b divides c plus s. One moment. Okay, when selecting the data source, the triple replica chunks usually have 2 replicas surviving. The scheduler can choose the source node as with a small expected completion time from 2 corresponding nodes. However, when selecting the destination, the number of candidates nodes is large and scanning all nodes is too slow. Thus, Dayu uses a dynamic convex hull algorithm to use a chance to binary searching the optimal node. The basic idea of dynamic convex hull optimization is map all candidates nodes to the points in a Cartesian coordinate system, using their available bandwidth b as a value of x-axis and the accumulated task size c as a y-value. Task T will also be mapped in this Cartesian coordinate system using 0 as x value and the minus size of task T as y value. So finding the node with smallest b divides c plus s is equal to finding the line connecting task point to node points with the lowest slope. To quickly find this, we can build a convex hull of all node points, and only the lower part of this convex hull is used, which is called lower convex shell, as a brown lines in the figure. The algorithms can find the optimal node through binary searching this lower convex shell. And after all the nodes is assigned within a new task, its accumulated task size is increases, and the scheduler should maintain a lower convex shell. Then comes the next task. To reduce the maintenance overhead, we further use bucket optimization to reduce the size of candidate points of lower convex shell. The plane of Cartesian coordinate system is divided into buckets as the dashed box in the figure. Only one point in each bucket can be the candidate node of the lower convex shell as the hollow point in the figure. Thus, the set of candidates only includes all hollow points instead of all points. Simulation results show that when the bucket size is set as 1 megabytes per second, the candidate set size is only about 1/23 of the original one. However, only using key technique 1, we found that the algorithm should carefully consider some nodes which have high available bandwidth but few available chunks. These nodes are called underemployed nodes. Dayu first identify these nodes and prioritize the tasks that can use these underemployed nodes as a source. After the source and destination node of each task is determined, Dayu should allocate bandwidth for it. Dayu proposed an iterative WSS algorithm to allocate bandwidth for tasks, and each task uses the allocated bandwidth to re-replicate the data. The goal of this algorithm is that all tasks complete as soon as possible in one time slot and introducing small interference to the foreground. The iterative WSS algorithms work as follows. In each iteration, iterative WSS conducts a similar procedure like the WSS algorithm. Their nodes have different available bandwidth on both incoming and outgoing sides, and there are tasks assigned on these nodes. The algorithm fairly allocates available bandwidth for all remaining tasks with the task size as weight until at least one link is fully allocated. If the bandwidth of a link is fully allocated, which means that the tasks transmit on it cannot obtain more bandwidth, then these tasks are removed as red tasks. Here comes the second iteration. Iterative WSS also conducts bandwidth allocation until one link is fully saturated, then move the corresponding tasks. Then for the third iteration, finally, no tasks can have more bandwidth than finish the allocation. After combining above three key techniques, we find some straggler tasks influence the quality of scheduling. And due to the fact that inaccurate workload estimation and so on, some tasks cannot complete in one time slot, and these tasks are called stragglers. If we do not reschedule these tasks will affect the quality of scheduling in current time slot. But if we reschedule them like a new task, stragglers, switching destination will lose its all progress. And to this end, Dayu first estimate whether these schedulers should change its destination, and for the stragglers change destinations, they have to be resent, and for the rest of the schedulers, they can be resumed with the source node change or the bandwidth changed. These four key techniques works as follows. First, the key technique 4 is used to classify different types of stragglers. Second, the key technique 2 is used to determine the transmission source of some tasks. Then, through the key technique 1, the source and the destination of all dispatching tasks are determined, and finally, the transmission rate of all dispatching tasks are decided by tag 3. Then all dispatching tasks are transmitted by the data servers. We implement Dayu on Pangu. The gray boxes are our modifications, and we introduce a centralized scheduler called Observer. We deploy Dayu on a 1,000 node cluster and trigger 15 terabytes data to recover. The baseline of this test our current Pangu recovery strategy, which randomly picks nodes to place data and allocates a constant recovery bandwidth on each node. The bandwidth is allocated as 30, 90, and 150 megabytes per second, called Pangu slow, mid, and fast, respectively. Among them, Pangu slow is the default setting on Pangu's production system. The evaluation is shown below. The x-axis is the recovery time, and the y-axis is the 90 percentile latency of the foreground traffic. The results show that compared to Pangu original strategy, Dayu has much advantages. Compared to Pangu slow, Dayu has the same level of low interference and is nearly 3 times faster in terms of recovery. And compared to the Pangu mid and fast, Dayu has same level of recovery speed, but Pangu mid and fast have far higher interference to the foreground. We also conduct some comparisons of Dayu with different algorithms, and the result shows Dayu outperforms them as well, and you can find the result in the paper. Next, to test the scalability of Dayu, we simulate data recovery with infinity tasks and test the throughput of different algorithms in 20 time slots. The baseline algorithms can be found in both research papers and industrial deployment. The result can be found in this figure. The x-axis is the cluster size, while the y-axis is the throughput. We find that Dayu can scale to 225,000 node cluster, and some algorithms can have same level of scalability, but their scheduling qualities are low. To conclude, through observations of production cluster, we find existing recovery scheduling failed to achieve both high speed and high quality. And we propose Dayu to use a time-slot-based protocol and a centralized scheduler, incorporates 4 key techniques in each time slot to achieve fast, high speed and high quality scheduling. The evaluation shows that Dayu outperforms existing solutions and has a good scalability. Thank you for listening.
Okay, questions?
Hi, Gala Yadgar from Technion. This is very nice work. Have you considered applying it to erasure-coded data centers?
No, it's a future work.
Thank you.
Abhinav there. You don't take into account the latency in trying to see the latency impact on the recovery, because you might be recovering from somewhere which is a little far off. Because the only dimension you're considering is the bandwidth and the size.
So I don't quite catch you, but you mean that so
because the recovery time can be impacted by the latency of the node where you're recovering from. So are like in your data center, all nodes have the similar latencies, or other latencies vary, or do you recover from like some other data center also?
Okay. So you mean that the latency is unnecessary in our evaluation?
Yeah, because you only consider the bandwidth dimension. The way you opt.
Okay, it's the latency of the foreground traffic. We have to show that the foreground traffic is not be interferenced by the background.
Okay. I see. Okay, thank you.
Okay, well, I'll ask my very standard question, which I noticed you collected traces.
Yes.
So can we get them?
So we have a meeting to talk about that.
Okay, I will be in touch.